Welcome, everybody. My name's Tim McKee. I'm excited to be here and talk a little bit about I3C and some of the advanced features that I3C does contain. So let's get started. We'll go over some of the main I3C bus features, kind of do a little bit of an overview of the standard use of I3C, and then we'll jump into some of the high data rates, multi-lane, features, as well as some of the timing features that have been incorporated into the I3C specification as well. So standard data rates and bus transactions, of course, we want to make sure everybody understands, the basics of I3C. If you don't understand the basics, of course, the advanced features aren't going to do you a whole lot of good. So I3C bus, basically it's a standard two-wire bus, SDA for data, SCL for clock. Your clock is typically driven by your controller and is held in a push-pull mode, while your data, the SDA, can be driven by either controller or target, and it switches dynamically between things like open drain, push-pull, high Z, high keeper. So as you can see on the top figure on the right, data is valid when clock is low. Data is valid when clock is high. Data changes when clock is low. We also have, uh, a, range of operating voltage from 1.2 to 3.3 volts. SCL max frequency 12.5 megahertz, which allows us a standard data rate of around 11.1 megabytes per second. And then there at the bottom on the left, you can see we also have reset states with SDA and SCL high. Uh, Different times on that uh, depict different bus states that are specified within the I3C specification. So with this is how we form our baseline for communication with I3C. So as far as transactions go, they are pretty well defined. You always have these indicators. You can see on the right side, we have a start, a repeated start, or a stop. Every transaction is going to start with the start indicator, followed by the 7 Tech 7E, which is the I3C broadcast address. And you can see in this transaction the different colors of segments, and that represents kind of the uh, different phases of this transaction with the ACK bit following, which is sent by the target. And then after that first start and the reserved address, you can see the actual right to target address is sent, followed by data. And then there's also a T bit, which for any write transaction is used for parity, which is as many of you know, would be an error detection mechanism. Okay. Also, you can have multiple writes, right? This repeated start indicator allows you to continue sending data or continue that transaction without restarting or having to go through that I3C broadcast address once again. You can just continue to send write information to specified targets. Now, when we switch over to a read transaction, everything stays pretty much the same. We still have our start indicator. We still use the repeated starts to continue communication. And then at the end, you can see there's the stop pattern. The biggest difference here between the read and the write is the T-bit. So whereas with our write data, the T-bit is parity, for read, it is an indicator that there is more data to come. So on this top figure, you can see whenever there's that T-bit 1, more data comes. Once you see that T-bit to 0, we get that stop indicator right after saying that we're done with that given transaction, right? So now we can also have mixed read and writes. So as you can see from this, that start and the reserved address, with what we say the I3C probe, is always at the beginning. And then through the repeated starts, we're able to continue sending read and writes. T-bit is following, depending on whether it is read and write as we depicted above, right? And the other side of this is, in these examples, we are doing specific targets. You can also do broadcast writes and group writes. So you can either send communications across the whole bus. You can also uh, organize targets into groups and then send that to just a specific group. Now, all of this is controlled with special commands that are specified within the I3C technology. We call them common command codes, or CCCs. Um, and so here in the bottom of this slide, you can see that the maximum amount of data that is transferred, that is actually variable. And we can set those lengths with these set MWL and set or get MWL, which is your max write length. And those are specialized commands that we use within I3C, and we'll get into those CCCs here now. So these common command codes is just a standardized communication set to really made to facilitate bus management and allow the management of the different functions and features within the I3C technology. As of right now, we have 57 CCCs defined. Some of them are optional, a handful of them are required, so they are needed for regular use and regular functionality of the I3C bus. But as you can see, a lot of them, somewhere around 40 of them, are optional features. And so they're there just to expand and make the I3C bus more feature rich. Um, these CCCs, some of them can be either broadcast or direct, so they can be broadcast to a small or large group of I3C targets, or you can have precision and just be going to individual targets with the direct CCCs. Um, so you can see in this table, there's all sorts of CCCs for different functions, whether it be multi-lane, entering into our high data rate modes, dynamic addresses, which are essential to the I3C technology, and we'll get into those a little bit more later. Bus events, routing, device-device transfers. These CCCs are really at the core of I3C and really what allow us to use and manage all the different functions that I3C does contain. Um, so how do these command codes work? Well, similar to our read and writes, they're well structured. The biggest difference here is after our I3C probe, the start and the 7TIC7E, you'll see an ACK from the target, but then a command code is sent. That command code depicts which CCC is being sent, and of course, those are all specified. And then following that command code, you see the repeated start with the addresses. Depending on whether it's a read or write, you're going to be using the T-bit once again. Um, and then for the broadcast command code, basically the same thing. We're just not sending that second address, which would depict a individual target or group of targets. We just stick with the broadcast. So for an example, setting the max payload size. Um, in this example, we use a direct CCC. You start off with the start command with the I3C broadcast address 7TIC7E. We receive an ACK from the target, and then the set MWL CCC code is sent. Um, from there, we get the T-bit and repeated starts, and then as you can see, we have an address, the ACK, and then the actual data, MWL MSB, MWL LSB, which will go forward to the target, set its max payload size, which will then be used by that target for ongoing communication. The same thing can be done with the write length, as you can see in the bottom. This is a broadcast example, so you can see that it's using the broadcast address instead of a specific address, which is how we depict the difference between the two. It's really, excuse me, really just a difference in which address that command is being sent to. Okay, so here we go with the dynamic addresses. This is uh, the responsibility of the primary controller during bus initialization. Every target must have a 7-bit address in order to function. So if you go back to I2C, these were static addresses, which can cause complications. And so in I3C, we moved to the dynamic address, which simplifies system management and drivers a lot. Um, there is still a sort of option to have a static address, since we do allow mixed buses. Basically, for an I2C device which has a static address, it would just use that static address and have it assigned during the dynamic address assignment procedure. Um, so as of now, there are 103 available addresses. There are also addresses that are not available, that are reserved, or that were used in I2C reserved. And so in order to maintain a sense of backwards compatibility, we don't use those addresses. However, if you're on what we call a pure bus, where there is no I2C targets present, those uh, addresses could possibly be used. Um, so here, as you can see on the right side, there are many CCCs dedicated to this address management, whether it be DA assignment, resetting, or setting a new, and then you can also do group addresses that can be assigned. And then, of course, a very important CCC at the bottom there is our get caps, which that is in order to get the capabilities of a target. So controller is able to send that. The target would then return data with all of the capabilities that it has, so that the controller and target can come to some sort of agreement as to what features can be used, right? So CCCs are a key feature and very highly used within this I3C standard. Okay, so that's the basics of the I3C bus, the communication and address assignment for initialization. Now let's get into some of the higher data rate modes. So this is for those maybe who have just started with I3C. Maybe you've only been really interested in I3C basic up until this time. Well, these high data rates and some of the other features that we're going to go into are the more advanced ones. Some of them are not supported in I3C basic, but we'll jump into them and try to do a bit of an explanation to get everybody a little educated on them. So as I just said, the high data rate modes are an optional feature. The purpose of them was to get more bits in the same clock, but doing that without increasing EMI, right? So no change in the max clock frequency, but more data um, throughput was the goal. These are all block-oriented transport, and we do use a CRC check on our HDR modes for safety requirements. So once again, we use our CCCs to enter the HDR modes. There's 7 uh, slots for HDR modes, but we only have 4 defined at the time. There's a HDR double data rate. There's a ternary for a pure I3C bus. That's a bus that has no I2C targets on it. And then there's a ternary for a legacy bus, which would have I2C on it. And then finally, we have an HDR bulk transfer mode. So those are our assigned modes right now. We do have 7 spaces, so there is room to grow, which is great. On top of that, we also make, we specified multiple data lanes. So instead of just the traditional 2-lane data bus with a clock and a data, you can add an additional data lane so that you have 2 data lanes, or even up to 4 data lanes. Obviously, more data lanes you have, the more throughput and more bits per clock you're going to get through. So the targets can also not support HDR modes. So when a bus enters an HDR mode, not all targets need to support that. They can actually ignore those HDR transactions. So why do we do the HDR modes? Well, we want to increase throughput. You can see on the left here the bit rates per the different modes on the right there with a very low bit rate. You can see the traditional I2C. To the left of that is our standard data rate. So our standard I3C getting close to that 11 to 12 megabits. And then all the way to the far end, you can see that HDR TSP, which is our pure for a bus without any I2C targets. You're able to get upwards of the 40 in megabytes per second. And down at the bottom, you can see the bit rates with the TSP and TSL is getting upwards of 100. So those HDR modes can definitely give you a huge boost. And on top of that, with the increase in multi-lane is just a multiplier on top of that. So with the combinations of these higher data rates, now going from your standard 11.1, you can almost get a 10x increase with the HDR TSP quad lane up to 100, right? So a lot faster capabilities there if your implementation requires it, right? Okay, so let's kind of dive into what are these different modes. So there's the ternary mode. In ternary mode, basically we transition the bus to become a two-wire signaling. Lines are driven by a transmitter, and the three states are possible with clock recovery. As you can see, those three states are here on the right side. So as I mentioned before, the two ternary modes are available. The pure for the no I2C devices present, and then the legacy inclusive, which allows those I2C devices. The biggest difference between them, there's some symbol sequences that are needed in order to hold I2C backwards compatibility. And so the TSL or ternary symbol legacy takes those into considerations. Also to note, these are not available in the I3C basic. So these are only available in the I3C full release version. But with this, obviously a much different communication style, you're able to get a more reliable bus and of course, much more data throughput. Okay, so that's our ternary. Our DDR and multi-lane, diving in a little bit more. So for double data rate, our HDR DDR, the trick there is what we're doing is instead of SDA only holding data valid while the clock is high, we now get valid data on both clock transitions or transactions. So without changing the clock speed, we're able to get twice as much data since we're now basically latching on either clock high or clock low, right? So that's the key for double data rate. As you know, as pretty obvious for the multi-lane modes, which are available in DDR and RTSP, what we're doing is we're adding extra pins, right? So of course it's specified and coordinated within these modes, but there's no secret to what we're doing here other than adding additional pins. This was something that it's an easy way, but of course pins are expensive, and so this we wanted to add the extra data rates as well to increase throughput so that implementers have options. If they've got the leeway in implementation to add more pins, they can get much higher throughputs. And then finally, we have our bulk transport mode. Bulk transport, this is one of the modes that uh, is available in BASIC. But the key here is we're sending 32-bit data blocks. So instead of our standard blocks, we increase that. We use a CRC 16 or 32 to increase reliability with still keeping that security enabled as well. Um, and also for this one in bulk transport mode, you're going to see sometimes where the target is going to drive the clock. So that is a unique scenario. Most of the time, the controller drives clock, but there are some unique cases, bulk transport being one of them, where we'll actually see the target drive clock. Um, so those are the basics of our HDR modes as well as multi-lane. Um, and so let's look at kind of the general HDR transmission. Once again, very well defined. You can see some similarities between our standard communication. Once again, we're starting with the start and the I3C reserved broadcast address. You get an ACK from your target, and then the enter HDR command, and followed by a T-bit. At that point, then you go to the HDR mode, and HDR in blue here at the bottom, you can see that's where the communication switches into this HDR mode. Now, the coding itself is specific to which mode you're in. So if you want details on the specific coding, you'll have to go into the specification, look at which HDR mode you're interested in, and you'll be able to see the coding for that. And then very important here at the end, we have a special hardware pattern in order to exit our HDR mode. And we'll get into the importance and what that looks like here. So why the HDR hardware exit patterns? Well, the reason we did this is because, like I stated earlier, not all targets are going to support HDR modes. So if you're in an HDR mode and a target is ignoring all those transactions, it wouldn't be very productive to send an exit pattern in that HDR mode as well. And so we had to come up with a different pattern that could be recognized by all targets and every device on the bus. Um, so there are two special patterns that are defined, an HDR exit and an HDR restart. Um, so the HDR exit pattern you can see over here on the right, patterns recognized after the fourth SDA falling edge while SCL is held low. So when any target, whether it's in the HDR pattern or not, recognizes this, it will know that there is an exit from the existing HDR pattern, and the idea is we'll return to the standard data rates and standard I3C communication. There's also a restart pattern, so an ability to remain in the HDR mode and continue communication, but with a different command. So either way, the patterns can be more recognizable and therefore allows this communication to happen, and still targets that don't support any of these HDR modes can still function correctly on the bus and not cause any issues there. So HDR DDR mode, as you can see, uses SCL as a clock. We also have these preamble bits. The preamble bits are gonna, their use will be dependent on uh, which mode is being used and which block is being sent. But this is the general breakdown of it. We've got 20 bits, two preamble, 16 bits of content, and then two parity bits at the end for security and error detection. And of course, as you can see, unlike the standard data rate here, we're seeing data latching on both the clock high and clock low. So we're able to effectively get twice as much data through here. Um, and here you see the preamble bits will be dependent on what is being sent. So for an enter HDR, you can see a preamble of a binary 0, 1 says that a command is going to follow. If you don't get that, then you know the command will not be following. Whereas for the read data, your preamble will depict whether a CRC or data follows. Same with the write data. So uh, these commands are the standard way that we do any communication within HDR DDR. So just to summarize, HDR DDR allows the double data rate. We do this without increasing the clock frequency, but by instead latching on both high and low of clock. It's a simpler hardware implementation. Instead of trying to increase the clock or drive a higher speed. This way, it's just a change in the data latching. We stick with the block-oriented transport with the CRC check in order to keep sure the safety and error detection, as well as the ACNAC at the block level there as well too. This mode is available in I3C specifications. It's mostly the ternary and the multi-lane, which are features that are only available in the full specification. So those are our HDR modes. Now let's move on to some of our other uh, specified elements, which is timing precision, right? So our main component in this is the in-band interrupt. So many of I3C's competing technologies do out-of-band interrupt, which they use a dedicated pin for interrupts. Um, we know that pins can be expensive, and so in I3C we designed an in-band interrupt that allows asynchronous data acquisition and processing um, by the target. So this is kind of a way for a target to get the controller's attention. Um, Basically what happens is the target issues this IBI request on the bus, and the controller would act the IBI request, and then we would go through, say, address arbitration, where um, the actual interrupt priority, due to the way I3C does address arbitration, interrupt priority would be based on address, with lower addresses having higher priority. By doing this, then sending this IBI request, the target is then able to communicate data over to the controller. So if that's a sensor sending data over, or many other target uses, now we're able to interrupt any or not interrupt the communication, but the target's able to send this interrupt, get its data over to the controller for processing, and it doesn't have to wait for any sort of polling or something like that from the controller. So timing precision. For sensors, of course, this is very important. Imagine, right, you're trying to track a moving object. Of course, you need to know distance, but if you want any sort of accurate readings in acceleration, velocity, anything along those lines, you need to have accurate timing. And so I3C, with the help of those IBIs, the in-band interrupts, we have added in different timing control mechanisms that allow the target and the controller to coordinate, and therefore improve our timing precision, whether that be through coordinating the target's activities or adding time stamps. So let's dive in. So we have an asynchronous timing mode. This is a way in which we add basically time markers. So the way this works is both the controller and the target um, uh, select basically a reference point. Depending on the timing control mode, this reference point could be different. I think in here you can see we have a reference point 1, TC1, and a reference point 2, TC2. Those are picked for this example at the end of the ACK and at the end of the T bit, right? So by um, uh, using different counters that are required for this timing control mode, by using those counters and adding these time marks, we're able to, with the help of some calibration, you can see down here on the bottom left, the calibration equation, but through these transactions, we're able to calibrate and improve the timing so that we can better tell when the actual target or the controller event happened, right? And so when the target sends its IBI, um, it will take its sensor data. It'll mark those spots or take count of those spots at the end of the IBI, or at the end of the ACK and the end of the T-bit, and it'll send that data within that IBI over to the controller. When the controller has those time markers, as well as its own, then we're able to use that calibration and come up with um, uh, a sensor sample point back at that C event. So this timing control mode, basically what we're doing, we're adding those time markers so that we can have a better sense of how long it's taking to get these communications across the bus. Okay, so that's our asynchronous time mode. What do we do in order to do that? Well, we have our CCCs that allow us to set up our time modes. The getX time, which is the get exchange time information. We can figure out which timing modes or timing control modes are supported, what rates, the accuracy and frequency. And then we have a setX time, which allows us to set which markers were being used and other information of that sort. So once again, we use these CCCs um, to set up and control the different features of the I3C bus. So how does it look like? Well, first off, you query the capabilities of the target. Step one, it's setting this get X time CCCs, and in return, we read all the data and we get the timing information back from the target. Next, you reset the timer and you initialize those timing markers with that set X time CCC. And then finally, you're able to get that time precise data with the markers included whenever that target is going to send the IBI from there. And then we're able to use that calibration equation and calculate for a more exact time. We also have the ability for synchronous systems. So this is more of the ability to bring multiple targets on a bus into a synchronous sampling time. Um, Main advantage here, we help prevent or against each target oscillator having its own drift or inaccuracies. It keeps the bus from getting too full with different polling, reading from different targets all at different times. And this is all achieved mostly by the implementation of a sync tick on the controller. And this is a tick that is sent out on the bus that allows the different targets on the bus to synchronize to that tick. So if we look at it, um, we still use the same type of CCCs in order to control this, the getX time to figure out what is capable, and then the setX time in order to distinguish the mechanisms that we'll be using for timing control. So for this synchronous timing control, we have this ST or the sync tick, which is sent out in order to synchronize the bus. We have a delay time, repetition, and then the output data rate. These are all different metrics basically to indicate how the bus will synchronize with itself. So let's look at an actual example of how this works, okay? Um, so let me try to explain this figure here really quick. On the bottom with the red, the three with the red line, that's our internal data of targets, right? You can see that they're on the top line, they're all sampling at different times, right? Data is available at different times. In the middle of the top and bottom, you can see we have a sync tick. Basically, this is indicating, okay, well, with our synchronous time events, we're going to set up the controller to send out this synchronization tick on the bus, and we'll see that every given time, which is determined by that ODT value that we have in the setx time. Okay, now the bottom line of these two is your synchronized, where everything is read in sync. So at the very bottom with the red bar, you can see the sensors are now sampling data all at the same given point, right? So this is after we've gone through the synchronization process. They've now aligned to the sync tick. So they now, internal to those sensors, they'll sample their data at the given time so that now all of that data is available for sending to the controller. Then as you can see on the top, the black lines, those are what is actually on the bus. So at first, it's all spread out, but then when we incorporate that sync tick and we synchronize with the timing control, now all of the data can be read out in blocks or sent over in blocks, and now the controller is going to get all that data in smaller time. So as you can see with um, uh, these lines at the bottom, there's all of the transactions are condensed into a given time, so we don't have as much um, random bus activity, right? So this is great for one, allowing more data to be pushed into a given time. It frees up the bus for other communication, but it also just allows the controller to get all of that sample data and use it all at the given time. So that's our synchronization events and everything for our I3C advanced features. I'd like to now pass it over to Michele, open it up. I saw we had the chat going quite a bit, so thank you for letting me speak, and look forward to questions. Go ahead, Michele.
Yeah, thanks, Tim. That was a great presentation. I presented some of this challenging timing stuff, very complex. That you did a great job in explaining a very, very complex feature there. Very complex, very powerful. How many different timing control modes are available in addition to the two that you presented?
So currently there are 5 modes specified. We have 4 asynchronous modes and 1 synchronous mode. The difference between the asynchronous modes uh, mostly have to do with the indicators and things of those lines. But of course, there's room for more as well too. So, but as of right now, we just have the 5 modes.
Okay. There is a question still on the timing mode. What is the precision we can expect from the synchronization mechanism?
The precision, I believe that's going to be pretty implementation specific as far as depending on the counters that are implemented.
Thanks again, everybody who attended. Thanks to Tim for giving this excellent presentation. You can get some more information, and also if you like to join, if you're a MIPI member, or if you're not, you might want to join MIPI. You're invited, to join the work group if you're interested, and you can download all the public specification.